Another classical example of a recursively defined function is the Fibonacci numbers. Okay, we can also call them as sequence instead of functions because they are defined over the set of integers, non-negative integers. So this example is slightly different from the previous examples because it requires us to define two base values. So we define the function value at 0 and 1. Okay, so instead of having one base values, if you recall from the previous slide, in case of the factorial function we need to define only one base case. Here, since the recursive expression is referring to two previous values or two past values of the function and has a memory of 2, in other words, this is the reason why we have to define two base values. Okay, so we define the value of the Fibonacci sequence at 0 and 1 to be the same as the time index 0 and 1 respectively. Now this expression we can use to find the further values of the sequence. For example, for n equals 2, you need the value of the sequence at 1 and at 0. Okay, so just put n equals 2 in this expression and you will see that to find the Fibonacci sequence at n equals 2, you need the value at 1 and at 0. Okay, and those values you are given because you define them as the base values of the sequence. And now you sum these values and you get 1 plus 0 equals 1. Okay, so now you have three values of the sequence. Now to compute the next value, you need the previous two values, which are f of 1 and f of 2, and you add them up. So they are 1 and 1, so they give you 2. To get the next value, you add the previous two. So 2 plus 1 will give you 3. To get the next value, you add 3 plus 2 and you get 5. To get the sixth value of the sequence at n equals 6, we add the previous two values at 5 and 4, which is 5 plus 3 equals 8.